You wake up on an ordinary Tuesday, and the first thing you notice is wrong before you can even name it. The moon is still up, in daylight, and it's the size of a dinner plate held at arm's length, hanging there like it's watching you. For 4.5 billion years, the moon has kept the same quiet routine, orbiting roughly 384,000 kilometers away, drifting outward by about 3.8 centimeters every single year. That drift is the reason astronomers roll their eyes at moonfall-style disaster movies. A stable orbit doesn't just decide to collapse on its own, but something out there, some rogue mass passing too close, some gravitational nudge nobody predicted, just knocked the moon off that leash, and now it's falling toward you. By the time anyone official says anything, half the planet already knows from their own phones before the news ever catches up. That's usually how it goes with things this big. The warning arrives sideways, through a shaky video from a stranger on another continent, hours before any agency confirms it. Some people don't believe it even when they're looking straight at it. A slightly oversized moon doesn't feel like an emergency. It feels like an optical illusion, the same trick that makes it look huge near the horizon. This time, it isn't a trick. 3 days before anything touches the sky, the ocean already knows something the rest of you don't. Tides that normally rise a meter or two start climbing 4, 5, 6 meters in a single cycle. Coastal cities that have never flooded in living memory go underwater on a clear, sunny afternoon because the water is answering a gravitational pull that grows stronger by the hour. Fishing boats capsize in harbors that were calm the day before. You might assume that being inland saves you from all of this. It doesn't. The ground itself isn't as solid as you think. Earth's crust rises and falls a little every day already, a bulge of solid rock pulled upward by the moon's gravity, the same way the oceans are, just smaller and slower, so slow you've never once felt it. As the moon closes in, that solid ground tide stops being invisible. Fault lines that have sat quiet for centuries start slipping. Volcanoes that haven't erupted in 1,000 years wake up together, on the same week, on opposite sides of the planet, because the same force is squeezing all of them at once. Your body still doesn't notice any of it yet. The planet already has. There's another detail almost nobody accounts for, and it comes down to a quirk you've probably never thought about. The moon is tidally locked, which means the same face has pointed at Earth for as long as anyone has been alive. As it spirals inward, Earth's own rotation keeps dragging new stretches of sky and new populations underneath that looming disk every 12 hours or so. If you happen to live somewhere the moon isn't currently overhead, you get a strange kind of mercy. A few extra hours of an ordinary-looking night sky while half the world already watches the end arrive. Somewhere above you, on the International Space Station, an astronaut is filming this. Not because they're brave, but because there's nowhere left to run to, and a camera is at least something to do with your hands. They have the best seat in the solar system for the worst event in human history, and they know it. Here's where almost every disaster video, including the one that probably brought you to this channel, gets the ending wrong. They show the moon slamming straight into the crust like a bowling ball dropped from orbit, one clean apocalyptic impact and roll credits. It doesn't happen that way. And once you understand why, the real version turns out to be worse. Every planet has an invisible boundary around it called the Roche limit, named after Edouard Roche, the French mathematician who worked out the math back in the 1840s. Cross inside that boundary and Earth's gravity starts pulling noticeably harder on the near side of any object than it does on the far side. That stretching, that tidal force, eventually wins against whatever's holding the object together. For a body built like the moon, rocky, layered, held together mostly by its own weak self-gravity, that boundary sits at roughly 9,500 kilometers from Earth's center. Earth's own radius is about 6,370 kilometers. Do the subtraction, and the moon never actually reaches you. It runs out of road around 7,000 kilometers above your head, and that's where the real story begins. You'd watch it happen in real time, and there's nothing slow about it. Cracks race across the lunar surface, the way a windshield splits under pressure, branching, multiplying, spreading in seconds instead of minutes. Chunks the size of mountain ranges peel away from the crust and drift into orbits of their own, tumbling, catching sunlight at strange new angles. Within a matter of hours, the thing that used to be your moon isn't a sphere anymore. It's a ring, roughly as wide as the old moon's diameter, glowing with pulverized dust, stretched into a pale band across a third of the visible sky. For one long moment, it might be the most beautiful thing you've ever seen. The band catches sunlight even after the sun sets where you're standing, so the night never really goes fully dark again, just dimmer, painted over in silver grey. Somewhere in a version of history where none of this happens, people are lying on beach towels looking up at a plain full moon and taking it completely for granted. Then you remember what a ring built out of moon-sized rubble does for an encore. Every fragment in that ring is still on a collision course. Gravity never cared that the moon broke apart. Breaking apart just means you've traded one impact for thousands, spread out across hours and days instead of a single afternoon. Some of those chunks are tens of kilometers wide, and individually, each one carries more destructive energy than the asteroid that ended the age of the dinosaurs 66 million years ago. That single ancient strike released something on the order of 10 billion times the energy of the bomb dropped on Hiroshima. Now picture dozens of impacts on that scale, landing one after another for as long as a week straight. The first major strike lands in the ocean, because water covers most of this planet, and the odds were never in your favor. The shockwave alone flattens forests 300 kilometers inland before the fireball even finishes climbing. Superheated steam and vaporized seawater punch straight into the stratosphere. The sound doesn't arrive as a bang. It arrives as a pressure wave that ruptures eardrums 1,000 kilometers away, minutes before the noise itself ever catches up to you. The second strike, hours later, lands on a continent this time, and it's worse in a different way. There's no ocean to absorb any of the energy, so it goes straight into the crust, throwing a curtain of molten rock and debris high enough to re-enter the atmosphere somewhere else entirely, starting secondary fires thousands of kilometers from the original crater. By the time the third and fourth strikes land, nobody's counting anymore. What used to be individual news events blur into a single continuous roar, felt through the ground as much as heard, a rhythm of distant impacts that never fully stops long enough for anyone to catch their breath. Seismographs designed to register a single magnitude 9 earthquake as a once-in-a-century anomaly are now recording dozens of them a day, back to back, until the instruments themselves start failing. By the third day, the sky stops being blue anywhere on Earth. Dust, ash, and vaporized rock from a dozen simultaneous impact sites spread into a haze circling the entire planet, and sunlight starts dimming the way it does during a total eclipse, except this eclipse never reaches totality and then ends. It just keeps going. Plants that depend on photosynthesis start dying within weeks, not months. The temperature crash that follows is the same mechanism scientists point to after the dinosaur-killing impact. Not the fire, but the darkness and the cold that come after, doing the slower, quieter half of the extinction while the fireballs get all the attention. Whatever survives of the debris field eventually settles into two fates. Some of it stays in stable orbit as a genuine ring, something no human alive today has ever looked up and actually seen circling this planet. The rest keeps raining down for months afterward, smaller and smaller fragments, a meteor shower that never fully stops, just fades from spectacular to routine to background noise you almost forget to look up at. Here's the part almost nobody brings up when they talk through this scenario, and it's the detail I find more unsettling than any of the fireballs. Earth doesn't just lose its moon, it loses the thing that's been quietly stabilizing it for the entire length of its history. The moon's gravity is what locks Earth's axial tilt in place, instead of letting it wobble chaotically. The way Mars's tilt has swung by tens of degrees over millions of years without a large moon to steady it. Take that anchor away, and the 23.5-degree tilt that gives you predictable seasons starts drifting, slowly, over tens of thousands of years, into something far less forgiving for whatever life eventually claws its way back from all of this. What strikes me most about this whole scenario isn't the fireball, or the ring, or even the extinction-level math stacking up impact after impact. It's that 7,000-kilometer gap between where the moon breaks apart and where the ground actually is. The idea that the single most catastrophic collision imaginable never technically needs contact to happen at all. The moon could erase almost everything you know without ever laying a finger on you. And somehow that's the part that stays with me longer than the fire does. Every big-budget disaster film wants you to believe the world ends in a single frame. One wall of fire, one hero's face, lit orange, cut to black. Real catastrophe doesn't work like that. And honestly, I think that's what makes this version harder to shake off. It isn't one clean ending. It's a slow unraveling that gives you just enough time to understand exactly what's happening to you before it's finished happening. So the next time you glance up at that same grey disk hanging in a completely ordinary sky, understand it's not sitting there by accident. It's held in place by a balance precise enough that nudging it even slightly is the difference between the quiet tides you grew up ignoring and a burning ring circling the planet within a single week. And if that's the kind of margin that separates a normal Tuesday from the end of the world, it might be worth wondering what other balances out there in this solar system are running just as close to the edge. Not the loud kind of catastrophe, the kind that announces itself with fire and noise, but the quiet kind, the kind that's already in motion long before anyone thinks to look up and check. That's exactly where this channel is headed next.